back to the CH1601 video series. This video will discuss how the reactivity of a carbonyl compound may be affected. As a reminder from the previous video, a general carbonyl-based nucleophilic addition reaction looks like this. The electron-rich nucleophile adds to the electron-deficient carbon atom of the carbonyl group. We make a new sigma bond at the expense of breaking the carbon-oxygen pi bond, and as a result, there is a change in hybridization from trigonal-planar sp2 to tetrahedral sp3. This general mechanistic pathway is what we will follow in all of the upcoming reactions in the carbonyl chemistry part of the CH1601 course. The nature of the substituents surrounding the carbonyl group can have an influence on two things: the reactivity of the carbonyl group and the stability of the addition product. Let's start with reactivity. In the carbonyl group, the difference in electronegativity between carbon and oxygen generates a slightly positive charge on the carbon atom. This is the reactive center of the carbonyl group. The more positive this carbon atom, the less stable the compound and the more reactive the carbonyl group. The extent of the positive charge experienced by the carbon atom can be influenced by the nature of the substituent groups. An electron-donating substituent, such as the inductively donating methyl group or a mesomerically donating benzene group, will push electron density onto the carbon and reduce its positive charge. This increases the stability of the compound and as a result decreases its reactivity. An electron-withdrawing substituent, such as the inductively withdrawing CF3 group, will pull electron density away from the carbon and increase its positive charge. This decreases the stability of the compound and as a result increases its reactivity. Now let's discuss the second effect of the substituent group on the stability of the addition product. In the reaction, we move from an sp2 hybridized trigonal planar compound to a sp3 hybridized tetrahedral compound. In the carbonyl compound, the substituents are 120 degrees apart, whereas in the addition product, they are approximately 109.5 degrees apart. This can be problematic if the substituents are large, bulky groups. Unfavorable steric clashes between the electron clouds of the large groups can occur. Smaller substituents, such as the hydrogen atoms, are unproblematic as there is no concern about steric clash. So why does all of this matter? Let's look at a real reaction in which we have a carbonyl compound reacting with sodium cyanide in a mixture of water and HCl to form cyanohydrin. It is standard to write the reacting species above the arrow and the solvent species below the arrow, as I have done here. So what's the nucleophile in this reaction? In this case, it would be the negatively charged cyanide ion. The nucleophile adds to the slightly positive electrophilic carbon of the carbonyl group, breaking the pi bond and giving rise to a new sp3 tetrahedral species. To obtain our final product, we react the negative charge on the oxygen with a proton, otherwise known as an H+ ion, from the HCl acid. The electron-rich nucleophilic oxygen donates a pair of electrons to the electron-deficient H+ ion, forming a covalent bond. We now have our final product, cyanohydrin. What happens if we go the other way from cyanohydrin to the carbonyl compound? If we treat cyanohydrin under basic conditions, such as sodium hydroxide and water, we can regenerate the carbonyl and cyanide species. What would be the mechanism for this case? We have a base, sodium hydroxide, which will react with the most acidic hydrogen in the molecule. The most acidic hydrogen would be the one attached to oxygen due to a greater difference in electronegativity. The base will accept the acidic proton, which places a negative charge on oxygen. This negative charge can push down to the carbon, which kicks out the cyanide leaving group. This takes us directly back to the reactants. So in this reversible reaction, which shares the same intermediate species, there must exist an equilibrium between the carbonyl compound and cyanohydrin. So how would you determine which side of the equilibrium is favoured? This depends on the nature of the substituents and what we discussed earlier in this video. Consider the starting materials and their cyanohydrin addition products. Reactivity decreases from formaldehyde to acetone as a result of the inductively donating methyl groups. Stability of the products decreases from formaldehyde to acetone as a result of steric clashes between the substituents. For formaldehyde, with a reactive starting material and a stable product, the equilibrium favours the right-hand side. For acetaldehyde, with a relatively reactive starting material and a relatively stable product, we will have relatively equal equilibrium. For acetone, with a relatively unreactive starting material and unstable product, the equilibrium favours the left-hand side. What would you expect for the equilibrium of this carbonyl compound and its cyanohydrin product? The inductively electron withdrawing substituent increases reactivity of the carbonyl compound, and the product is relatively stable, so the equilibrium favours the right-hand side. And what about this compound and its cyanohydrin product? Although there will be steric clash in the product, the two electron withdrawing substituents hugely increase the reactivity of the carbonyl compound, so the equilibrium massively favours the right-hand side in this case. Being able to compare starting material and product stability to predict equilibrium constants is an important skill for CH1601 students to understand, and more examples will be provided in class. Try the quiz now to test your understanding of carbonyl reactivities and product stabilities.